Greetings everyone. Welcome to this Midas Civil webinar on footbridge modeling and design on vibrational analysis. I am Anuj Asati. So I am working at Midas R&D Center, India, which is based at Navi Mumbai. So today I will be conducting this webinar session. So as the topic for today's webinar is footbridge dynamic analysis. So let's start. So talking about the contents of the webinar. So first we'll see the introduction of footbridge dynamic analysis, and then we'll move on to footbridge design specifications and challenges. So what are the challenges which engineers face during the design or an analysis of footbridge. Then we'll move on to the basics of dynamic analysis, and then we'll see the codal requirements as per Eurocode. So while talking about the design of footbridge, Indian code does not specify any guidelines for a dynamic analysis. So that's why we'll be referring to Eurocode for the requirements for dynamic analysis. Then we will see how to generate a truss bridge model in Midas Civil. So we will not be going into details of modeling. So I will just briefly cover how I generated the model using Truss Wizard and how you can generate it in your end. If you want a detailed kind of tutorial, step-by-step tutorial on how to generate the model which we have used in the webinar, kindly let us know in the comment section or kindly mail us at Midas support global support.midastuser.com. Okay, so if you have any questions, kindly hold it till the end of the webinar. So if possible, if time permits, we'll be taking some of the questions at the end of the webinar. It may not be possible to answer all of the questions due to the restraint of time. So what we will do, we will take a note of all the questions and we will reply them via email. Okay, so post generation of the model, we will see the stability and dynamic response of the structure. Okay, so let's start today's webinar. So coming to the introduction, so the main question that comes to mind, why dynamic analysis of pedestrian bridges is necessary. So why we want to do dynamic analysis of pedestrian bridges? So as you know that footbridges are more sensitive to dynamic loads such as pedestrian loads. And dynamic analysis is nothing but analysis of time varying external loads. The type of vibration which comes on the bridge may cause discomfort to the pedestrians as well as deterioration of footbridge structural integrity. And the type of dynamic loads which will be coming on the bridge will be such as walking, jogging, and steady state crowd loading conditions. And the primary objective of the dynamic analysis is to determine the effect of dynamic loads on the structure's dynamic response and its influence on the users. Okay, so this is the main gist of why we perform dynamic analysis of pedestrian bridges. So we'll be looking this into more detail. So now moving on. So now we will look at major design specifics and challenges which is faced by engineers in design of footbridges. So the first thing, the major challenge is the geometry. So as you know, these days the footbridges which are being designed are people want them to be more aesthetic. So due to that, they are going for more complex geometries for the design of footbridges. So such as they can go for tied arch or curved or very complex geometries, as you can see in the images. So that is a major concern which we need to consider while the design of bridges. So this type of complex geometry involves complex analysis as well. Then coming to the second part, the material used in the for the construction of footbridges is also a lot of variety of materials are being used. So starting from masonry, stone, steel, concrete, timber. So all these types of materials are used in the construction of footbridges. So that is also it's also a challenge. So we need to consider the types of materials as well for the footbridge design. Moving on. Now the second thing which we need to consider is the structural robustness. So as I already mentioned, that the footbridges are designed as very light bridges. They are very slender, very flexible. So what happens, at the same time we need to ensure the structure to have sufficient strength as well as stiffness to maintain the stability. So as we know that the magnitude of the pedestrian loading is very less as compared to that of a highway bridge. However, if we see the ratio with that of the self weight, the magnitude of loading to that of the self weight, the ratio is higher in case of a footbridge than a highway bridge. So due to this, the critical load combinations are different in case of a footbridge than that of a conventional bridge. Moving on. Another challenge and the design specific for footbridge is the attention to stability and vibration issues. So this is a very important case. So I will be giving you an example of this in a moment. So what happens so if we see a highway bridge, so medium and short span bridges does not have much impact due to vibration or due to stability. But when we come to footbridges with natural frequency which are on the lower side, it leads to instability in the lateral response, and vertical vibrations may also cause discomfort to the users. To emphasize more on the effects of vibration, what you see in this slide is the image of a Millennium Bridge. Many of you might be knowing this Millennium Bridge. So this is a Millennium Bridge in London. So this bridge is very important in terms of dynamic analysis. Actually, this was the first bridge where synchronous lateral excitations were noticed. So basically what happened, in an effect, with the bridge lurched on one side. So due to the lurching of bridge on the one side, the pedestrians changed the way they walk in anticipation of the bridge movement. So to balance themselves, they spread their feet apart, causing a lateral force on the bridge. Basically what happened, all the pedestrians which were standing on the bridge, they spread their feet apart, causing a lateral excitation in the bridge. And all of them did it at the same time, which caused a synchronous lateral excitation. So the situation is similar to what soldiers marching in a lockstep, but this happened in the lateral direction rather than the vertical direction, which happens in case of soldiers walking. So due to this synchronous lateral excitation, the bridge failed. So as I told you, so I have emphasized much on this aspect, like we need to do a dynamic analysis of foot-over bridges. So now moving on to basics of dynamic analysis. So we are all aware of the dynamic analysis, that how it is dependent on the mass, structural damping and structural stiffness. So just to give, so for our bridge, basically the damping which we will be considering for our bridge will be 3%. So this value has been taken from the Eurocode for steel bridges with high resistance bolt. Okay, So moving on. So the pedestrian action on footbridge. What are the things which we need to check while doing the dynamic analysis of the footbridge? So we need to check it. So in Eurocode 1991 to 2003, UK National Language 2.44, two distinct analysis has been mentioned. So one is to determine the maximum vertical deck acceleration and its comparison to comfort criteria, and the second is to determine the likelihood of large synchronous lateral response. So we will be taking a look when we need to go for these two types of analysis. Once we will discuss this in more detail. Then coming to loading. So the type of loading which is specified in the Eurocode for comfort criteria check is first the walking pedestrian, the second is the jogging pedestrian, and third is the crowd steady state condition. So the damping ratio we will be considering 3%, as our bridge is a steel bridge, steel truss bridge, and the time forcing function for walking, jogging and crowd steady state is specified in Eurocode 1991 part 2. Now we'll see the Eurocode requirements for the bridge. So recommended crowd densities for design. So for our case, we are considering it as a C bridge class. So we are considering an urban route subjected to significant variation in daily usage. So for this, the group size for walking we need to consider it as 8, and the group size for jogging we need to consider as 2, and the crowd density we need to take it as 0.8. Okay, so now moving on. So as I told you, Eurocode specifies the forcing function for walking, jogging and crowd steady state. So this is given in National Language 2.44.4. So this is the function according to which we need to create forcing function for walking and jogging. So here this F naught is nothing but the amplitude which we need to consider for force calculation. So this is 280 newtons for walking and 910 newtons for jogging, and the speed for walking is 1.7 meter per second, and for jogging it is 3 meters per second. And this frequency, we will be calculating this frequency. This frequency for loading we will keep it same as that which we obtained for the fundamental natural frequency of the structure. So basically what we will be doing is we will be checking the structure for resonance condition. So we will be keeping the frequency of my load equal to that to the frequency of my structure, so that the resonance condition may occur. And so this will be the worst scenario which will happen on my bridge. So if my bridge passes in this worst scenario, so I can ensure that whatever other loading which is coming on the bridge, my bridge will be safe. Then the other parameters such as n is already we have discussed. The value of n is the group which we need to consider, group of pedestrian which we need to consider for walking and jogging, and gamma. So it is the reduction factor to allow the unsynchronized combination of action in the pedestrian group. So this need to be calculated as per the graph which I have shown in the next slide. Then so all these things need to be calculated as shown here and in the next slide. Now for crowd loading function, so as you can see, the crowd loading function is pressure function, that is kilonewton per meter square function. Okay, so here so now we are going to see this in detail, how we have calculated these functions. So not need to worry about if you are not able to get it right now. So we are going to calculate all these things in detail in the later part of the webinar. So next is this relation for KFV and frequency FV, and this is the graph from which we need to calculate the reduction factor gamma. Okay, so moving on. So this is the today's example which we'll be using to do the dynamic analysis of the footbridges. So this is a steel truss type of bridge, and the total span is 48 meters, and the number of cross beams are 12, which are spaced at 4 meters each. So while the creation of this geometry, there are basically two ways. So one is the basic way where we create the nodes, and from nodes we create elements. So the nodes and element approach. But what we are going to discuss is an easier approach, which is creating the structure using Truss wizard. So this is the speciality of Midas. So we have different wizards to create the geometry. So what wizard does is, so as the conventional way is to create the nodes, and from nodes we create the elements, and from that we create the whole structure. So basically in wizard we just need to give the configuration of the structure. So configuration in the sense, what is the span, what is the type of truss I want to use, what is the height of my truss, what are the types of cross members which I want to use. So I just need to specify all these things, and the structure, the whole structure will be created for me. So to show you in the software, let me just open the software here once. So now if you see, so this is my structure which we have created here. So based on this, so how we can create is, you just need to go to structure, and here in base structures you can see this is the truss wizard. So this type of truss I have created. I just need to give the type of truss I want, the type of cross members, and the total span. So the total length will be, in our case, will be 24, and the number of panes will be 6. The bridge is symmetric. Height for our case was 4 meters. So like this. And if I need vertical members, so just by giving the inputs and by changing these things, I'll just press OK, and a geometry similar to this will be created. And using the single pane, I will create the other side of my truss, and I will connect it as required, and the whole geometry will be created like this. So if we do it in a conventional way, it will take a lot of time for an engineer to create such a geometry, but by using wizard, that modeling time will be reduced drastically. Now this is how the modeling can be done. And the second approach, how we can go about this, is by importing it from CAD or Revit or Tekla. So this may be useful in large structures where there are many elements or the geometry is very complicated. So Midas Civil allows you to import import the files from Revit or Tekla, which we can directly use it as an analytical model. Okay, so this is one more approach to easily model in Midas Civil. So now we'll be going into the main part of the webinar. So how to conduct dynamic analysis of the footbridge. So first we will see the workflow of how to conduct a dynamic analysis. So when we are conducting a dynamic analysis on a structure, so the first step for any type of dynamic analysis is to perform a free vibration analysis on the structure. The purpose of performing free vibration analysis is to find the fundamental natural frequency of the structure, plus how are the mode shapes of my structure. So how my structure is going to be excited and what are my fundamental natural frequencies. So this is my first step. So using these fundamental frequencies, I will be creating my time history load cases, load functions, and I will be applying those load functions on my structure. Okay, so once I have done the free vibration analysis, so based on that I will determine my pedestrian time forcing functions, and I am going to apply those forcing functions on my structure. How we are going to apply that, we will see in a moment. Then once we have applied the forces, we will analyze and we will find the peak acceleration of the structure. So this peak acceleration we need to compare with the codal limit of peak acceleration, and if the limit is exceeded, then we need to apply some vibrational control measures on the bridge to bring down the peak acceleration of my bridge within limits. So this is the workflow, how we perform the dynamic analysis of the footbridge. So moving on, so first step is to perform a free vibration analysis. So as we all know, free vibration, so the equation is exactly same as which we saw for dynamic analysis, but in this case the force is 0 for free vibration analysis. So as I already mentioned, the main purpose of this is to obtain the fundamental natural frequency of my structure. Okay, then if we see as per Eurocode, we need to check for comfort criteria if the fundamental frequency of the deck is less than 5 Hz in the vertical direction, and if the frequency is less than 2.5 Hz in the horizontal or torsional vibration. So once we are going to perform the free vibration analysis, we'll find out the fundamental natural frequencies in Z and Y direction. Now we need to compare those fundamental frequencies with these values. If it is less than 5 Hz in Z direction, then I need to perform the comfort criteria check in Z direction, and if it is less than 2.5 Hz in in lateral or torsional direction, then I need to perform a comfort criteria check in lateral and torsional direction. Okay, so let me take you to the software now, where we are going to perform the free vibration analysis. Okay, so this is my structure for which I am going to perform the free vibration analysis. So let me give you a brief of how I have modeled this the whole bridge. So these are my truss part. So these two are my trusses, and the bottom, basically how I have modeled my deck, that will be interesting. So let me show you. Yeah, so basically how I have modeled this is, if I show you, so these three are my main stringer beams which are going to run throughout the bridge, and these 12 members are my cross girders. So these are my main elements of my bottom of my deck. So, and the others cross girder, these are my cross girder. And now how I have modeled the slab is, so basically the slab I have applied this, if you see my loading, so here I have applied the dead load of the slab as on my stringer beams. So basically how I have modeled, so these are the dummy slab elements which I have created on the deck, basically to transfer whatever load I have applied on my deck, it will be equally distributed on my stringers. So basically the material for which, so this are the dummy slab. So if you can see here, my weight density of my slab, I have kept it as 0. And if you see the section, so basically 0.25 is the depth of my slab and 2 meters is the spacing of these slab elements. Okay, so like this I have modeled my deck. So yeah, so this is the modeling of my deck. Now I will just activate all. So this is the structure. So now the first step before doing eigenvalue free vibration analysis is to convert my self weight into masses. So basically we need to convert the self weight to masses for our free vibration analysis, and the second step is to convert my load to masses. So here I have converted my SIDL as the self weight and crash barrier loads to nodal mass. So why I am converting these loads to nodal masses? Because these are permanent loads. So these loads will be there, these loads will be applied on the structure throughout its life, and those are permanent loads. So whenever the earthquake will happen, these loads will be acting on the structure. So that's why when my pedestrian loading will be acting on the structure, these loads will be present on the structure. So that's why I am converting these loads into nodal masses. So once you press OK, you can see these loads are converted into nodal masses. Now my structure is ready for free vibration analysis. So I will just show you the definition which I have given for free vibration analysis. So here the type of analysis I have selected it as eigenvector analysis, and I have selected Langko's method, and here the number of frequencies I have kept as 15. So now the question arises, how to decide the number of frequencies for which I need to do this free vibration analysis. So basically the number is decided by the mass participation. So the total mass participation, various codes suggest that the total mass participation should be greater than 90% in the major direction of excitation. So our case, like in Z and Y direction, should be greater than 90%. So I have checked for my structure for which we are doing dynamic analysis. For 15 number of mode shapes, it was greater than 90%. Okay, so based on that we should decide these number of frequencies. So now my structure is ready for free vibration analysis. So let me just analyze this. So yeah, so the free vibration analysis is over. So let me just show you the results of free vibration analysis. So this is how my structure is deforming for first mode shape. So as you can see, this is in major Z direction. So the major response is in Z direction, and yeah, so similarly if I show you for second mode shape, so this is the major response for this mode shape is in y direction. Okay, similarly we can see for other mode shapes as well. So now I will show you the summary of all the modes. So now you can see, so these are the 15 mode shapes which we have considered, and these are the frequencies. So cycles per second is nothing, it's nothing but hertz. So this frequency for my first mode shape is 2.1695 hertz. And if you see the mass participation, so now you can see it is dominant case in the z direction. So in vertical direction, this is my dominant mode number 1, and for that my natural frequency is 2.1695. Now coming to if you see mode shape 2 is dominant in y direction, for which my mass participation is 71%. So the natural frequency for mode shape 2 is 2.5786 hertz. Okay, so these are the two dominant mode shapes in z and y direction, for which I need to check it if it is satisfies my Eurocode criteria or not. Okay, so coming back to my presentation now. Yeah, so as we have seen, the major frequency 2.16 in z direction, it was 2.1695. so for this check is required, and in transverse direction, in y direction, I was getting the frequency as 2.6, around 2.6 hertz. So it is greater than 5 hertz, sorry, 2.5 hertz. So in horizontal direction, I don't need to perform the comfort criteria check. Okay, so we need to perform a comfort criteria check in the z direction. So now that we are done with our free vibration analysis, now we need to move on to time history analysis of the structure. So here we have to do it in 3 steps. So first we need to define our time history analysis load case. Then we need to define our time history load function, and third we need to apply that on our structure. So there are various ways to apply a time history function to the structure. So we will be looking into that. So what are different ways we can do that? So now I'll just give you a brief of the time history analysis in in Gen. So in Gen, basically it's both. It is same in both Midas Civil and Midas Gen. Time history analysis is almost same. So if you see analysis type, there are 2 types, linear and non-linear. So our case, we are going to do linear modal time history analysis, and analysis method is modal and direct integration. So in modal analysis, we need to do our response by a free vibration and modal analysis, and based on that it will do the time history analysis. And in direct integration, we don't need to perform the free vibration analysis. So that is the basic difference between the two modal and direct integration method. Then coming to the time history type, there are 2 types, transient and periodic. So in transient, basically what transient means is when the load type is not repetitive, as in the load function occurs only once, like it is not repetitive. So for example, earthquake load. So the earthquake load is not periodic or repetitive kind of load function. It is a transient type of load function. For that case, we need to go for transient type of time history analysis. But coming to periodic type of time history analysis, when the load is repeated after a particular time, the load case is repeated. For example, machine load. So machine loading is a repetitive periodic kind of loading, And another example in our case will be a crowd steady state loading. So it is a sinusoidal loading, so it is a repetitive kind of loading, so that is also a periodic type of loading. So for us, walking pedestrian, jogging pedestrian load case will be transient type of load cases, time history analysis. And for crowded steady state condition, we need to go for periodic time history analysis. So for walking and jogging, we need to go for linear modal transient time history analysis, and for crowd steady state condition, we need to go for linear modal periodic time history analysis. So now let's go to the software, and we will define these time history load cases. Okay, so now that we are done with our free vibration analysis, so now we need to define time history load cases. So for that, I need to go to load, I need to go to dynamic load, I need to go to load cases, so if I press add, so now the first case which I will be defining is walking. It will be linear, modal, transient. Now the end time. So how to decide this end time? So basically the total length of my bridge is 48 meters, and the speed for for walking, it's 1.7 meter per second. So if I calculate the time for traveling from one point to the other point, it comes out to be 28 seconds, around 28-29 seconds. So basically this end time I need to keep more than 29 seconds. So I can keep anything more than 29 seconds. It should not be less than 29 seconds, as the total motion of walking pedestrian will not be captured. So for our case, I will be considering 40 seconds, and the increment will be 1 and 0.01. Now the damping ratio for all modes, I need to consider 3% as mentioned earlier. Press OK. Yes. Similarly, I need to create for jogging. Analysis type is linear. Analysis method is modal, transient, and type I will keep it as 40. And damping ratio I will keep it as 3%. Now again I need to create for crowd. Linear, modal, but now in this case it will be periodic. So end time I need to specify, I will keep it as 40 seconds, and damping 3%. So like this I need to define my time history load cases. Now going back to the presentation. Now that we are done with the load cases, we will move on to time history force functions. So basically now, as I already mentioned, the code specifies this type of forcing function which need to be created for our bridge. So to create this forcing function, I took help of Excel to create this type of forcing function. So let me show you that Excel file which I have created. So now in our case, the total span of my bridge is 48 meters, and the damping which need to be considered is 3%, and the frequency is 2.1695. So now this frequency I am keeping it as same as that of my natural fundamental frequency of my bridge. So as I told you earlier, I want to create a resonance condition in my bridge, so that which will be the most critical case, and if I am able to satisfy the comfort criteria for the most critical case, my bridge will be safe for all the other cases. Okay, and based on that, we will be creating this forcing function. Then the value of n, as mentioned earlier, is taken for class C type of bridge. For walking it should be 8, jogging 2, and walking 1. Okay, and based on all these values we created these force functions. Now this is the total force function. Now for creating the function I have divided it by 3. As I have showed you earlier, in my bridge I have 3 stringer beams along the span. So I will be dividing whatever total load coming on my bridge, I will be dividing that and applying it on those 3 stringer beams. So that's why I have taken it divided by 3. Okay, similarly for jogging. Now coming to crowd loading function. So this is the crowd loading function specified as per the code. So this is kind of a sinusoidal function. So we can create a sinusoidal forcing function in Midas gen as well. So to create that, this is the template according to which we can create a sinusoidal function. So if I'm comparing both these functions, so this total part is A for my forcing function which I need to create, and this F is equivalent to frequency here as well. Okay, so like this I need to create this forcing function. So basically if I want, I can create the forcing function as the above one as we created here, but you can see it is almost comparable. So I can create using directly giving the value of A and frequency. Okay, so for that I just need this value of A. So this value of A, force, that is the amplitude of this function, this we have calculated here based on the inputs, the same inputs. The span is 48 meters, width of my walkway is 6 meters. So based on that I have calculated the area, the damping, and frequency 2.1695. So based on that we have calculated this A value. Again, if you see here, I have divided it by 3. So basically I have converted it into separately for my 3 stringer beams. But as you can see here, so this A value is kilonewton per meter square. So this is a pressure loading, as I mentioned earlier as well. So what the code specifies for crowd condition, it is a pressure loading, but we are going to apply it as a point load. So in that case we need to convert it into point load. So as I mentioned earlier, the spacing of my cross beams is at 2 meters, and so the spacing is at 2 meters, and the influence area of each stringer, so based on that I have multiplied it by 2. I have calculated for each point on my on my stringer. Okay, so now I will create these functions in Midas gen. So I'll just close this. So now time history functions. So add time function. So the first one I will create for walking. So this is a force function. Okay, so now I'll just, so there I can either import, if I have a .thd.sgs file, so I can import, or if I want to do, suppose I'm doing a earthquake analysis or time history for any major earthquake. So you can see in the database it has all the major earthquakes which has happened, so I can select it from here. Or in my case now I am going to use Excel, so I am going to copy paste my force values from here in Midas. Just copy this for force function. Now I'll just paste it here. So now you can see, so my forcing function I have created here. So I will just press OK. Similarly, I need to create for jogging. This is also a force type function. Again, I will copy from Excel. And paste it here. Okay, so like this for walking and jogging I have created. Now for crowd, as I told you, we'll be creating a sinusoidal function. So I'll just name it as crowd. So a value I will take from here as 0.0125. Okay, this is also a force type function. So 0.0125. Kindly mind the units as well. So in what units you have created your load and in what units you are going to enter. So this may impact the analysis in a huge way. So be consistent with the units which you are using and which you are using for calculation, which you are using in the software and with the calculations. Frequency, I will keep it as 2.1695, which is my fundamental frequency of the structure. So I will just redraw the graph. So you can see this is my forcing function which we are going to use for our crowd loading. Okay, so I will just press OK here. So now these three functions are created for my structure. So I need to apply this function to the structure. So as you can see here, there are various ways to apply this function to the structure. So either I can give ground acceleration, I can apply as dynamic nodal loads, or I can apply as time varying static loads, multiple support excitations. So there are various ways, but in this case what we will do, we will go with dynamic nodal loads. Okay, so now how to apply this dynamic nodal loads? So basically we need to give the arrival time of each and every dynamic nodal load which we are going to create. So basically we are going to simulate the walking condition, jogging condition and crowd condition. So based on the velocity of the pedestrian for walking and jogging, we need to create different loading points at different point arrival with different arrival times. Okay, so again for that I took help of Excel to create dynamic nodal loads. So I'll just show you how I have created these dynamic nodal loads. So for that, so now as I told you, for walking my speed is 1.7 and for jogging it is 3 meters per second, and the frequency is the fundamental frequency of the bridge, which is 2.1695. Now we need to find the step length. So for step length is nothing but your speed into your time period, and time period is nothing but 1 upon frequency. So based on that I found out the step length for walking as 0.785359 and for jogging as 1.38 meters, and the arrival time is nothing but your step length divided by your speed. So the arrival time for my bridge is 0.46 seconds. Okay, so based on that I've created these nodes and these step lengths. Okay, and this is my arrival time. So I will just show you how to create this dynamic nodal load in Midas Gen. So if I'll just, so my first node is 139. So on that I will apply. So for function for walking, here also I will select walking in z direction, -1, arrival time is 0, the node to be applied is 139. I will select it and I will apply. So I will just switch off the hidden view. So similarly for node number 1001, so the next node at 0.78 meters, so now arrival time will be 0.46 seconds. Okay, rest of the things remain same. I will apply. So now there are so many nodes on my bridge. So this is for stringer 1. Similarly I need to find for stringer 2, stringer 3. So it will become very tedious if I go and apply for each and every node. So for that again we will use Excel. So now I know the nodes for which I need to apply. I know the arrival time. So based on that we can create an input somewhat like this, and we can just paste it. Okay, so now similarly I have created this input for our bridge. So I have created these two nodes. So similarly I need to create for the rest of the nodes. Just copy and I will paste. Okay, similarly I will paste for jogging as well. Okay, so this was done for stringer 1. Similarly I need to do for stringer 2 as well. Okay, similarly for stringer 3. Okay, so now that you can see here, we have created the dynamic nodal loads for walking and jogging condition. So now I need to create for a crowd condition, crowd steady state condition. So what the code says is for crowd steady state condition, the arrival time should be 0 for all the nodes, and the speed should be considered same as that for walking, which is 1.7 meter per second. So I need to select all the nodes which I have created for walking condition, and on that I need to apply my crowd loading condition with the arrival time as 0. Okay, so let me do that. So here I will select my crowd loading function. Arrival time will be 0, -1 direction. So now I will select the nodes. So the nodes will be all these nodes which I have done for walking. So 120. Okay, so I have selected the nodes now, so I just need to apply now. So now, as you can see, I have applied all the dynamic nodal loads for walking, jogging and crowd condition. Okay, so now my model is ready now for analysis. So we have defined all the time history load cases and loadings. So now I just need to perform the analysis. So just let's perform. Okay, so my analysis is complete now. So let's first view the time history results. Okay, so let's see the first acceleration. So let's see first displacement in the z direction. Legends, animate. So total increment time I will give 0.5 seconds. Now apply. So the maximum deformation, so let me just turn it to mm. I need to apply again, sorry for that. Yeah. So maximum deformation in z direction is 0.588 mm. So it's lower on the lower side. And let me see the acceleration, maximum acceleration in z direction due to crowd loading. So units again, so it is around, I think 0.1 meter per second. Let me see here in deformations. So similarly for other load cases can also be seen for jogging and walking, for for crowd condition, for different steps. I can see the results. Okay, so let's see the maximum acceleration in dz direction for THmax crowd. So now here we can see, let me change the unit to meter. Yeah, so we are getting it as 0.11 meter per second square. Okay, so now if I want to see the graphs for time history function, so to see the graph we need to go to here, time history graph, define function, okay, add new function. So acceleration in z direction due to crowd. We forgot to see for which node we are getting the maximum acceleration. Let's check that once. So displacement contour, crowd, acceleration, dz direction, legends. Yeah, so I am getting maximum acceleration at node number 2030. So we will generate the graph as well on this node. So sorry, no, not this one. Define function. So this will be 2030 and the name will be so this will be acceleration type ground in DZ direction. Reload case as crowd. Okay, back. So on horizontal axis it will be time, so this will be acceleration Z. Okay, so I'll just generate the graph. So now this is my acceleration in Z direction. You can see it is 0.11 around 0.11 meter per second square, and if you see for what time, total time it has run, sorry, similarly what I can do for I can get the same similar function for jogging as well. So acceleration ground DZ direction, so this will be jogging. Okay, so let me just close this once. Time history graph. Okay, now I will select, let me select jogging first, only jogging. Let's select time. So now this is for my jogging curve. So now you can see here maximum acceleration is 0.08 meter per second square. Okay, so now I will add this load as well. So now you can see here it is not very clearly visible, but both the graphs are overlapped here. So red one being my jogging curve and green one being my crowd condition. So now you can see here for crowd condition I am getting more acceleration. So maximum acceleration is 0.1093. Similarly, I can define various functions here based on different nodes, different load case. I can compare different things here. So I can compare displacement with, so all the parameters I can compare based on, I can select and I can compare on a same graph. So this is a very useful feature here. So similar, now that we have found out the maximum acceleration which I am getting for my crowd condition at node number 2030, which is 0.1093. Now I need to compare this with the codal provisions. So in code, how much is the maximum acceleration permissible in Z direction? Okay, so I will take you back to the presentation now. Okay, so these things we have covered already. Yeah. So this was for this type of, so now for our case for jogging we were getting 0.1 meter per second square, 0.11 meter per second square peak acceleration due to a crowd loading condition. Now if you see as per the National Annex 2.44.6, peak acceleration is defined as this alpha limit, which is 1 into k1, k2, k3, k4 So these are dependent on various parameters you can check from the code. So for our case, we are getting alpha limit as 0.91 meter per second square. So as you can see, for our bridge it is 0.11 meter per second square, which is less than the limit. So but there are many cases when this limit may exceed than alpha limit. So now we have covered the major things of this webinar. We have covered the basics of dynamics and how to do dynamic analysis. Now we have one more thing to cover. When this limit is exceeded, what we need to do. So there are various vibration control techniques. So I'll just be giving you a brief overview of those techniques. We will not be going into detail. So that is a whole topic in itself. So suppose when it is more than what is anticipated, the acceleration is more than the limit. So in that case, what we can do is we can modify the mass. So as I already told you, footbridges are very light bridges. So what we can do, we can modify the mass. What will it do? It will improve the dynamic response of the bridge as a consequence of the increased modal mass. So so for steel ribbon structures, this approach works very well. The second thing what we can do is modification of frequency. So basically how we are going to modify frequency is by altering the stiffness of the structure. So this type of case are usually applied when this type of approach is usually applied when the frequency is on a border range. Okay, but this is a very tedious process, as you need to modify your designs, full designs for this approach. The next thing which we can go for is modification of damping. So there are various damping systems available in market. So such as viscous dampers, tuned mass dampers, pendulum dampers, tuned liquid column dampers. So based on the requirements and whichever fits in your case, that kind of damping system can be applied. The most popular are viscous dampers and tuned mass dampers. So this is a whole topic in itself, damping systems. So we are not covering that in this webinar. Kindly let us know if you want a webinar on damping systems. So we will be conducting that. Okay. So what we have, so I'll just briefly cover what we have covered in today's webinar. So first we saw the various challenges which engineers face in design of footbridge. Then we saw the basics of dynamic analysis and the various codal requirements for Eurocode for dynamic analysis. Then we moved on to free vibration analysis of the bridge, and then we performed we've defined time history, load case, load function and dynamic nodal loads, and we applied on the structure and saw the response of the structure, peak acceleration, and compared it to the codal limits. So this was I tried to cover as much as possible about the dynamic analysis. I hope you enjoyed this webinar and it was helpful for you. Kindly let us know if you have any questions on globalsupport.midasuser.com. Either reply it in the comment sections or kindly mail us to globalsupport.midasuser.com. So we will be getting back to you with the answers. And thank you for your time, and thank you for attending this webinar. Hope this was useful to you. So here I am going to end this webinar. Thank you.